Hello students, I welcome you in today's session of physics. And in physics, as you can see here, I am going to take your chapter number 22, which is the polarization of light. Clear? So in this chapter, first we will discuss what we have to study. So you can see here, this is the syllabus. And in this syllabus, you have to study about the polarization, plane polarized light, Brester's angle is most important one, uses of plane polarized light and polarites. Clear? I hope you understand it. Now first we talk about what is light waves are transverse. Here first one. According to the Huygens wave theory, light travels from one place to another in the form of waves. Clear? Now waves are of two types. I hope you know very well what is longitudinal waves and transverse wave. So in longitudinal waves, the vibrations of the particle of the medium takes place in the direction of the propagation of the wave. This is the longitudinal waves in which the particles of the medium vibrate in the direction of the propagation of wave. While in transverse wave, the vibration of the particle of the medium takes place perpendicular to the direction of propagation of wave. So the sound waves are longitudinal. Clear? Huygens had initially assumed in his wave theory that the light waves in ether are also longitudinal. So he explained many phenomena like reflection, refraction, interference and diffraction of light from his theory. But in 1690, when Huygens himself discovered the phenomena of polarization, he had to discard the idea of assuming light waves as longitudinal because it could not explain the polarization. So after nearly 140 years, Fresnel proved that light waves are not longitudinal but are transverse. So this is the important one, that light waves are transverse in nature but not longitudinal. Now you can see here there is an experiment performed for this. You can see from the figure 1, which is the A1 and the B1, both are the two figures given here in this one. So what's going on in here? The transverse nature of a wave can be tested by a simple mechanical experiment. These are the experiment you can see A and B. Let the horizontal string passing through the two slits S1 and S2. Here you can see in the figure A, this is your figure number A. This one is slit S1 and this one is slit S2. So a horizontal string is passing through the two vertical slits S1 and S2. You can see from the figure first A. In the cardboard pieces be held by two persons A and B in their hands. Now let us suppose the person A move his hand up and down parallel to the slit S1. This gives rise to transverse wave in the string. Means if a person is standing at point B, move his hand up and down, then there is a transverse wave developed in this string. So this gives rise to transverse wave in the string, the particles of the string vibrating parallel to the slit S1. So if the slit S2 is parallel to S1, the vibration passes through S2 and reaches the person B with undiminished amplitude. If however S2 is rotated become perpendicular to S1, so the vibration are stopped by S2 as the displacement of the particle is now at right angle to the length of S2. So the string therefore does not vibrate beyond S2. So in the intermediate position of the slit S2, the vibration are partially transmitted and partially stopped. That is, they reach the person with undiminished amplitude. So thus we concluded that, or we can say that as the slit S2 is rotated, the amplitude of the vibration varies. Here you can see in the figure B, we rotate the slit S2, and here they are both are in the parallel condition. So what happens if we rotate the slit S2? So the amplitude of the vibration varies. Clear? Now had the vibration being longitudinal, that is parallel to the length of the string, they would have passed through the slit S2 in all angular position of S2. So we can conclude that if the amplitude of a wave produced in a string passes through the slit S1 and S2 varies. So when S2 is rotated, then the wave passing through S1 is transverse, and if on the other hand the amplitude remains same, the wave is longitudinal. Now there is an experimental demonstration of the transverse nature of light. I told you about the Maxwell's equations, which I taught you in the electromagnetic waves chapter. So using the Maxwell electromagnetic theory of light, a light wave is an electromagnetic wave which consists of electric vector E and the magnetic vector B. So both vibrating in mutually perpendicular planes which are also perpendicular to the direction of propagation of wave. Clear? So the optical effect of light is due to the vibration of the electric field vector. So such wave do not require any material medium for the propagation, as I told in the chapter electromagnetic waves that I taught you. So obviously transverse in nature. Now the transverse nature of light wave can be demonstrated by a simple experiment you can see here. This is the figure number 2 in which we are performing and demonstrating the transverse nature of light from this experiment. So what's going on here? Let us suppose P1 and P2 are the two tourmaline crystals which are so cut that their axes lie in the plane. Ordinary light rays are allowed to fall normally on the crystal P1 and P. So if P1 is rotated, you can see from the figure A and B, about the light ray as axis there is no change in the intensity of the emerging light. So from this we concluded that the vibration of the electric vector E are taking place in all direction in a plane perpendicular to the propagation of the ray of light. Now the second crystal, which is P2, is placed between the crystal P and the I in such a way that the axes of P1 and P2 are parallel. Then the intensity of the emergent light is maximum, so you can see from the figure 2a. But if the crystal P2 is rotated on its plane, then the intensity of the light reaching the eyes goes on decreasing. Clear? So when the axes of the two crystals become perpendicular to each other, the intensity of the emergent light become maximum. You can see from, minimum, figure B. So it follows from the experiment that the vibration of electric vector E in light waves are transverse. So if light waves were longitudinal, then the intensity of the light emerging from P2 would not have been affected by the rotation of one crystal relative to the other. Clear? Now this is the explanation of the experiment, polarization of light. So if in an ordinary light waves, the vibration of the electric vectors occurs symmetrically in all possible directions in a plane perpendicular to the direction of propagation of wave. Clear? This is written here. So when the light wave is incident on a tourmaline crystals, only those vibrations of the wave emerges from the crystal which are parallel to the axis of the crystal. You can see from this figure. And the remaining vibrations are stopped by the crystal. So thus after emerging from the crystal, the vibration of the electric vector of light wave occur only in single direction. So in a plane perpendicular to the direction of propagation of wave, not in all direction as before. So such a wave is called plane polarized waves. Clear? What is plane polarized wave? In which the vibrations are passed in a particular direction, or you can say that parallel to the axis of the crystal, or you can also say that its another name is plane polarized, or it is called as linear polarized wave, and this phenomena is called polarization of light. Fine. Now in the experiment, the polarized light emerging from the first tourmaline crystals fall on the second crystal. So when the axes of both the crystals are parallel to each other, then the vibrations emerging from the first crystals also pass to the second crystal, and the intensity of the emergent light is maximum. But when the axes of the crystal are mutually perpendicular, then the vibration emerging from the first crystal are stopped by the second crystal, and the intensity of the emerging light becomes zero. So in this position, the crystals are said to be crossed. Clear? You can see from this situations from this figure 2a and b. These figures are easily determine what's going on or what we are talking about. This one. Clear? So here is a definition given there. The first crystal which polarizes the light wave is called polarizer, while the second crystal which examines the nature of the light emerging from the first crystal, whether it is polarized or not, is called analyzer. Clear? I hope you understand it, what is polarizer and what is analyzer. Now we are coming to what is unpolarized and plane polarized light, the second one. This one we are talking about what is unpolarized and plane polarized light. So light wave are transverse, as you know very well, I told you. So hence the vibration of the electric vector must occur in a plane perpendicular to the direction of propagation of light. Now each vibration in this plane is perpendicular to the direction of propagation of the wave. From the figure number 3, you can see here, in ordinary or unpolarized light, the vibrations of the electric vector E occur symmetrically in all the possible directions in a plane perpendicular to the direction of propagation of light. Therefore, when ordinary light is passed through single rotating tourmaline crystals, there is no change in the intensity of the emergent light. The reason is clear that in all orientations of the rotating crystals, the probability of the occurrence of light vibrations parallel to the axis of the crystal is same. Hence, the intensity of light emerging from the crystals is same in all orientation of the crystal. Now, what's going on in plane polarized light? The vibration of the electric vector, which is your E, occur in a plane perpendicular to the direction of propagation of light and are confined to a single direction in the plane, do not occur symmetrically in all possible directions. Thus, the vibration become asymmetrical about the direction of propagation of light. So, after emerging from the tourmaline crystal, the vibration of the lights electric vector are parallel only to the axis of the crystal. Hence, the light is plane polarized. Clear? So, if this light be seen through the another rotating tourmaline crystals, there will be a change in the intensity of the light. It will completely cut off. Then the crystals are crossed together. Now, this is a representation of the polarized and unpolarized light. You can see from the figure number 4. This is given here. Clear? So, I'm not going too deep. Just see the figure, and if you have any doubt, kindly ask me. The first one is the unpolarized light. The second one, vibrations which are parallel to the plane of paper and perpendicular to the direction of propagation. And the third one is a vibration perpendicular to the plane of paper. Plane of vibration and plane of polarization of plane polarized light. What are the plane of vibration and plane of polarization? This is also the important one. So you have to see this. So plane of vibration, what is? This one here, the plane of vibration and the plane of polarization of a plane polarized light. So first we talk about what is plane of vibration. The plane containing the direction of vibration of the electric vector and the direction of the propagation of light is called the plane of vibrations. Here you can see in the figure 5, O dash, this one is the plane of or plane polarized light is the direction of propagation of light, and ABCD is the plane of vibration. You can see from the figure, this is the plane of vibration. Now, what is plane of polarization? The plane containing the direction, clear, of propagation of light and perpendicular to the plane of vibration is called the plane of polarization. You can see here from the figure, plane of polarization is your EFGH. Clearly, there are no vibration of light in the plane of polarization, which is your EFGH is the plane of polarization. Clear? Now we will move to polarization of light by reflection, that is Brewster's law. This is the most important topic of this chapter. What is Brewster's law? Clear? This one. So this thing we will discuss in our next lecture, which is your lecture number 2. Till that, do study. Thank you, class. Thank you very much.